So what we're doing here, we've got a general object. We've got 2 points. We've got a point B, and that's going to be our point of fixity, or the point about which we're interested in determining the moment. And then we've got another point A, and there's a force being applied to point A, so this is the point of application. The basics of what we're doing here is we're showing that if you've got a force applied at a specific point B, you can actually change that to a force at another point with a moment associated with it, or a couple. And so that becomes useful because it helps us later when we're looking at static equilibrium. We'll be able to figure out what the reactions are at B for a force applied at A. So that's kind of why we're doing it, and just work through the process of how we transform this from having a force at B to having a force applied at A to having a force applied at B. And because we've moved this force, what we also have to do is to apply a moment to the point B. So you can imagine that. And so what we're going to end up with, we'll work through it and you'll see what we'll end up with. So just to check that we're not changing anything as we go along, what I'll do is I'm just going to write down the sum of the x components, sum of the y components, and the sum of the moments. And so we have got here, let's just add a couple of things to the diagram. So that force F, it would have an x component, Fx, and a y component, Fy. I'm not really going to worry about signs in this example, and you could always put your axes so that everything ended up positive. But I just want to work through it a bit quicker. And so we're also, what I'm going to do when I'm finding the moment, I'm going to use the first method we used where we trace the line of action. We're not going to use x and y components for the moment. We're just going to trace the line of action of that force and find the lever arm to the force itself. I think this is about 22. And so this will be about 68 to get the lever arm. Okay, shortest distance to the line of action, and it's always at right angles if it's the shortest distance. And that's the lever arm D. I've labelled that Fx, I haven't labelled that yet, so that's Fy. Cool. So let's just think about what we've got here. Pretty simple. The sum of all the x components in this system is just Fx. There's only one force in the x direction. The sum of all the y components is just Fy. And the sum of all the moments is just equal to F times D. So that's the only moment we've got. Let me just change this to black. Okay, so now what we're going to do is we're going to try and get rid of this force at F, and we're going to get a force at B instead. And because we've moved that, this has a lever arm, so there must be moment about B as well. So let's have a look at how they do that. It's a bit like a conjuring trick, like the pea under the cup or whatever. But it all makes mathematical sense. So let's just copy all of this and move it across here. Just pull it up this way a wee bit. Move it across a wee bit. Let me just rub out these just now because we're going to check these again. So what we can imagine is, imagine if we just drew a force at F, draw that force at the point of application at B. So we were to, let me just check how long it is, just so the diagram looks nice, about 14 or something like that. So suppose we move that to there, and it's got the same size. What would now happen is you'd have 2Fx, because you've got two of these forces, you'd have 2Fy. The moment would still be the same, Fd, because this force doesn't have any moment about the point B, because its line of action goes through that point. Now, we don't want to change anything. We want to figure out how we can find the equivalent force couple system, so the equivalent force in a moment about this point B. So we don't want to change anything, and so we can't do that. But what we can do to make it all balance and make sure we don't change anything, is we can add an equal and opposite force in the other direction. So 14. That's also F. Oh, sorry. And so that means, so these two forces are going to cancel out because they're equal and opposite. And so in terms of force components, all we've got is what we started with. And so that hasn't changed anything, what we've just done there. Not working. Get rid of that. So we're now back to the same situation as we had in the first case. So far, so good. Now, what we can see here is we've now got a force and a couple. So a force here and a couple here. Let me just highlight that couple. So you got this force and this force. Those make a couple. So they're parallel lines of action, opposite directions, separated by a distance of d, and that distance d is the lever arm. And so what we could say then, and remember it is still the case that the moment of a couple is just force times distance. Okay, so it's one of the forces times the distance between them. So rather than draw it like that, remember I mentioned before, sometimes rather than draw the forces themselves, what we do instead is we just show the direction of rotation and write on what the moment of the couple is. And so we could get rid of that and get rid of that. So this is all going to disappear. Oops. And then what we would end up with, because we don't want to change this, is we just say the moment at that direction. So making sure I think about which direction that couple's rotating this thing in. So it's like that, and that moment is FD. And so we've ended up, we started with a force at A. We're looking for what would be the equivalent force and moment at B. Well, the equivalent force and moment at B, you would go through this process, you draw equal and opposite forces at the point B and find the couple, the moment of that couple. So you can just draw the force at B and then indicate the magnitude of the couple, just using a little arrow to show that there's a couple there, and the magnitude of that is just the force times the distance from the original point. Now, you could do the same thing in reverse. If we started and we were given, I might just change that to red so it's the same color as the original. You could start at this point and you could work backwards. And so if you're given a force and a couple at B, or a force and a moment at B, and you want to find the equivalent at A, you could work back through this process and you could end up with this situation here where you've got a force acting on any point there, and now you just got a pure force with no couple. Let's try some examples of those. I think is the easiest way to take it forward. So we'll go and try some examples of those now.